Hey, welcome. Today we're going to tackle something that sounds kind of complicated. Systems of linear inequalities, but is actually an amazing visual tool for making decisions. Seriously, think of it like creating a map that literally shows you every possible good choice you can make when you've got limits, like a budget or a deadline. So let's start building that map.
And believe me, this isn't just some abstract math class stuff. As this quote points out, this has serious, real-world muscle. An investor uses inequalities to map out their entire strategy. They're thinking, okay, I will not accept a loss greater than this, and I will lock in my profit if it's at least this much. They're literally defining their field of play, their region of success, before they even make a move. That's the kind of power we're talking about. So here's our game plan. First, we'll get down to the basics. What even is an inequality? Then, we'll turn that idea into a picture by graphing one. After that, we'll level up and combine them to solve a whole system, learn how to find the exact corner points, and then, finally, we'll see how this all plays out in the real world. Okay, so first things first. Every map has a language, right? For the decision map we're building, that language is all about the inequality. You know, an equation is super strict. X equals exactly one thing. But a linear inequality? It's way more chill. It describes a whole range of possibilities. Think about keeping food fresh. The temperature can't be one single number. It has to be less than or equal to some maximum temperature. That entire safe zone is what an inequality helps us map out. So these are the four symbols that do all the heavy lifting. The top two, less than and greater than, are strict. They don't include the number itself. But the bottom two, they're inclusive. See that little line underneath? That means or equal to, and trust me, that tiny little line makes a huge difference when we start drawing. All right, theory's done. Let's actually turn these symbols into a picture. This is where the magic really starts to happen, where we take a rule and create the first part of our decision-making map. The process here is actually super logical, which is nice. We'll start by drawing a boundary line. Think of it as our fence. Then, we figure out if it's a solid fence or a dotted one. And finally, we just test a point on one side to see which entire region we need to shade in as our solution zone. Let's walk through this one together. We're graphing x plus 3y greater than 3. First thing you notice, right? The line is dashed. Why? Because our symbol is strictly greater than, not or equal to. The points on the line don't count. Now, how do we know where to shade? We pick a super easy point to test, like home base, 0, 0. Plug that in, you get 0 plus 0 is greater than 3. So, is 0 bigger than 3? No way, that's totally false. And because it's false, we shade the entire region on the other side of the line. Everything in that shaded area is a solution. Oh, and before we move on, here's a fantastic little pro tip to help remember horizontal and vertical lines, because they can be tricky. Just remember hoi vux. Hoi, horizontal lines have 0 slope and are always y equals a number. Vux, vertical lines have an undefined slope and are always x equals a number. It's a simple little trick that'll save you a lot of headaches. Okay, so we've totally nailed graphing one inequality. But let's be real, life is rarely that simple, right? Usually, there's more than one rule. So now we're going to see what happens when we bring a second condition into the mix and find out where their solution worlds overlap. And here's our second rule for this problem. Negative x plus y has to be less than or equal to 6. And right away, you should be noticing that or equal to sign. That's a huge clue for what's about to happen on the graph. And boom, here is where it all comes together. We've added our second inequality, and just like we thought, it has a solid line because of that or equal to part. Now, the solution to the whole system. It isn't just one shaded area or the other. It's that darker, overlapping part where both conditions are true at the same time. We call this the feasible region, and it is the complete map of every single possible correct answer. So we've got our feasible region, which is awesome, but you can kind of see the problem, right? Looking at a drawing isn't always precise enough, especially at those corners where the lines cross. We call those vertices, and sometimes we need to know their exact coordinates. And this is a fantastic, real question from a student. What if the graph is huge or the numbers are messy? A hand-drawn line isn't going to give you a perfect answer. How do you find that exact intersection point with 100% accuracy? And the answer is, you stop relying on your eyes and you start trusting the math. You don't have to guess from the picture. You can calculate the exact spot. As our source material says so well, the vertices are found by solving pairs of the equalities of the boundaries. Trust the math. It will show you the way.
And it's actually really straightforward. Here's all you do. You take the two boundary lines from our graph, and you just treat them as a system of normal equations. Now it's just a classic algebra problem. You solve this system, and the xy answer you get isn't an estimate. It is the exact, precise coordinate of that vertex. No drawing necessary.
Okay, so we've drawn the map, we've found the exact street corners, but who cares, right? Why does any of this matter outside of a math class? Well, let's bring it all back home. I mean, think about something as simple as budgeting. You've got $40 for art supplies. Paint is $6, brushes are $4. That inequality right there, 6x plus 4y less than or equal to 40, perfectly describes your world of options. If you graph it, you can see every single combination of paint and brushes you can afford. The same exact logic applies to investing, or to a logistics company planning delivery routes with limits on time and fuel. This is the math that helps people find the absolute best outcomes when they have to follow a set of rules.
And that really brings us to the core idea. The big takeaway is that so many of our choices in life are just about balancing multiple constraints: time, money, resources, you name it. These inequalities, they aren't just lines on a graph. They're a way of thinking, a way to map out your options. So the question I want to leave you with is this: what system of inequalities is shaping your next big decision? Thanks for tuning in.